Tonight, we drift toward one of the most extreme worlds in our solar system, Venus. Once similar to Earth, it slowly became a planet shaped by heat, pressure, and time. A place where familiar rules no longer apply and balance was quietly lost. Welcome to the Orbit for Sleep channel. Let us follow the orbit of science and drift gently towards sleep. You arrive at a place that feels familiar at first. The sun is still there, distant but present, casting a steady light across space. Venus moves calmly along its orbit, closer to Earth than almost any other planet. From afar, it looks bright, smooth, almost gentle. Nothing about its appearance suggests urgency or danger. As you drift closer, the sense of calm begins to loosen. The surface below is not glowing like molten rock, yet the heat is everywhere. The temperature here settles around 475 degrees Celsius. This heat does not come and go. It does not depend on day or night. It surrounds the planet evenly, pressing into everything that reaches the ground. This detail quietly breaks an expectation. Mercury orbits much closer to the Sunday. Mercury receives far more direct sunlight, yet Mercury cools dramatically at night, dropping to extreme cold when the sun sets. Venus never cools. Its surface remains hotter than Mercury's, even though it lies farther from the Sunday. The reason is not the sunlight itself, but what happens after the sunlight arrives. Venus is wrapped in a massive atmosphere made almost entirely of carbon dioxide. This gas behaves like a thick thermal blanket. Sunlight passes through the clouds and warms the surface. The surface then releases that energy as heat. Instead of escaping back into space, the heat is absorbed by the atmosphere and sent downward again. This process is known as the greenhouse effect. On Earth, the greenhouse effect keeps the planet warm enough for liquid water and life. On Venus, the same mechanism has grown far beyond balance. Over time, more heat led to more atmospheric gas, and more gas trapped even more heat. Scientists describe this as a runaway greenhouse effect, a cycle that reinforced itself until cooling became impossible. The result is a world where metal softens, electronics fail, and mechanical systems shut down simply from exposure. Spacecraft that reached the surface in the 20th century survived only minutes before heat overwhelmed their instruments. This was not because Venus is violent, but because it is relentlessly stable in its extremes. A simple comparison helps ground this scale. A kitchen oven set to its maximum temperature reaches about 260 degrees Celsius. Venus is nearly twice as hot, everywhere, all the time. No shelter, no shadow, and no rotation brings relief. Venus shows that distance from the sun is not the final judge of temperature. Atmosphere matters. Balance matters. Small differences, allowed to grow unchecked, can transform a planet completely. What looks calm from space can become the most hostile surface in the solar system, not through sudden catastrophe, but through slow, irreversible change. The number comes first before any image fully forms. 475 degrees Celsius. It appears precise, almost clinical, yet its meaning only becomes clear when it is translated into experience. On Venus, this temperature defines everything. It is not a peak reached at noon, and it is not a momentary spike during volcanic activity. It is the baseline condition of the surface. The ground, the air pressing down, and every object resting there share this same heat continuously. To understand this scale, everyday materials offer useful reference points. Lead melts at 327 degrees Celsius. Tin melts at 232. Aluminum begins to weaken structurally, not far above 400. At 475 degrees, metals lose strength, seals fail, and lubricants evaporate. Electronic components stop functioning long before melting occurs, as internal connections break down under sustained heat. This explains why Venus is often described as a planet that melts machines, even though its surface is not covered in liquid metal. The destruction comes not from flames or explosions, but from exposure. Heat slowly enters every joint, wire, and casing until function becomes impossible. The atmosphere plays a central role in maintaining this condition. Dense carbon dioxide transfers heat efficiently, preventing local cooling. Even areas that receive less sunlight remain hot because heat circulates through the thick air, equalizing temperature across the planet. There are no safe zones, no temporary refuges. Historical attempts to study Venus made this reality clear. In the 20th century, Soviet landers reached the surface with heavy insulation and pressure-resistant shells. Despite these precautions, internal temperatures rose rapidly. Instruments continued sending data for only minutes before shutting down, overwhelmed not by mechanical impact, but by heat alone. The number also carries geological meaning. At 475 degrees Celsius, chemical reactions behave differently. Rocks release trapped gases. Surface minerals change structure. Water cannot exist in any liquid form. Any trace of moisture would instantly become vapor, then break apart under ultraviolet radiation. This temperature turns Venus into a stable system, locked into one state. Cooling processes that operate on other planets are effectively disabled. Without oceans, without weather cycles capable of carrying heat away, the surface remains fixed at this extreme. 475 degrees Celsius is not simply a measurement. It is the condition that defines Venus itself. It marks the boundary where familiar matter stops behaving in familiar ways, and where exploration shifts from engineering challenge to fundamental limitation imposed by physics. Heat alone does not define the surface of Venus. Alongside it exists another condition, quieter but just as decisive. Pressure surrounds the planet like an invisible weight, pressing downward without pause. At the surface, Venusian atmospheric pressure reaches about 90 times that of Earth. This means the air itself exerts as much force as standing nearly 900 meters below the ocean's surface on Earth. The comparison is useful because it replaces abstraction with sensation. At that depth, water presses against the body from every direction. On Venus, air performs the same role. This pressure is created by the sheer mass of the atmosphere. Carbon dioxide makes up almost all of it, forming a dense column of gas stretching high above the surface. Gravity pulls this mass downward, and the result is a crushing load that never lifts. Pressure changes how materials behave. Seals that work perfectly on Earth begin to deform. Lubricants thicken or break down. Moving parts experience increased friction because the surrounding gas resists motion. Even simple actions, such as a mechanical arm extending or a valve opening, require far more energy than they would under Earth-like conditions. Historical exploration revealed this limitation clearly. In the 20th century, landers sent to Venus were designed with thick metal shells, similar to deep-sea submersibles. These vessels were built to resist collapse rather than impact. Despite this, pressure combined with heat caused rapid failure. Once internal cooling systems lost efficiency, rising temperatures finished what pressure had already strained. Pressure also alters sound and motion. The dense atmosphere carries vibrations more effectively than Earth's thinner air. A falling object would descend slowly, not because gravity is weak, but because the air resists movement like a fluid. Wind speeds can be modest, yet the force they exert is immense due to atmospheric density. This environment creates a paradox. Venus does not require violent storms to be destructive. Calm conditions are enough. The steady pressure presses into every surface, every joint, every enclosure, turning time itself into a destructive force. On Venus, machines are not crushed in a dramatic instant. They are slowly overwhelmed. Pressure ensures that nothing rests lightly on the surface. Everything bears weight. Everything yields eventually. The failure does not arrive suddenly. When a lander touches the surface of Venus, it is still intact, still functioning, still sending information. For a brief window of time, technology and environment coexist. This window is measured in minutes. The primary cause is not a single overwhelming force, but the combination of heat and pressure acting continuously. Even before landing, a spacecraft has absorbed heat while descending through the dense atmosphere. By the time it reaches the ground, internal temperatures are already rising. On the surface, cooling becomes almost impossible. Heat flows inward from every direction. The surrounding air is hotter than the maximum operating temperature of most electronic components. Unlike Earth or Mars, there is no cooler air to draw heat away. Fans and radiators provide little benefit because the environment offers no temperature gradient to exploit. Pressure accelerates this failure. Thick atmospheric gas pushes against seals, joints, and insulation layers. Any microscopic weakness becomes a pathway for heat transfer. Materials expand under temperature stress, breaking tight tolerances designed under Earth conditions. Electrical connections drift out of alignment. Sensors lose calibration. The history of Venus exploration made this reality unavoidable. In the 20th century, Soviet Venera landers were engineered specifically for survival on the Venusian surface. They used spherical pressure vessels, heavy insulation, and limited onboard systems to reduce heat generation. These landers did not attempt long missions. Their goal was to endure long enough to transmit a few images and measurements. Even with these precautions, survival times were brief. Minutes stretched into slightly longer intervals, but the outcome remained the same. Internal temperatures climbed steadily. Once critical thresholds were crossed, systems shut down one by one. Not violently, but irreversibly. This pattern reveals an important distinction. Venus does not destroy machines through sudden events. There are no surface explosions or constant quakes tearing landers apart. The planet simply does not allow equilibrium. Any object introduced to the surface is pushed, thermally and mechanically, toward failure. In this way, Venus acts less like a battlefield and more like an endurance test that no machine can pass for long. The environment does not need to change. Time alone is enough. On many worlds, heat comes and goes. Day brings warmth. Night allows release. Motion creates cycles that soften extremes. Venus exists outside this pattern. Once heat arrives at the surface of Venus, it has nowhere to go. The planet rotates extremely slowly. A single day on Venus lasts longer than an entire Venusian year. Yet even this extended night offers no relief. Darkness does not bring cooling. Temperature remains nearly constant, locked at extreme levels. The reason lies above the surface rather than below it. Venus is sealed beneath a thick, opaque atmosphere. Carbon dioxide dominates the air, forming a dense barrier that blocks heat from escaping into space. Infrared radiation, the form of energy the surface emits after warming, is absorbed and re-emitted downward again and again. On Earth, oceans, winds, and a thinner atmosphere help redistribute and release heat. Warm air rises, cool air sinks. Energy moves across the planet and outward into space. Venus lacks these balancing mechanisms. There are no oceans to store excess heat. There is no efficient pathway for energy to leave the system. Clouds complicate this process further. High above the surface, Venus is covered by thick layers of sulfuric acid clouds. These clouds reflect much of the incoming sunlight, yet paradoxically, the surface remains intensely hot. The reflection limits new heat entering, but it does nothing to remove the heat already trapped below. The planet reached thermal equilibrium long ago, at a temperature far beyond habitability. This condition did not form overnight. Scientific models suggest a slow transition. As temperatures rose, any surface water evaporated. Water vapor itself is a powerful greenhouse gas. Its presence accelerated heating, which led to more evaporation, reinforcing the cycle. Eventually, ultraviolet radiation from the sun broke water molecules apart, allowing hydrogen to escape into space. What remained was a dry world incapable of cooling itself. Without water, without plate tectonics recycling carbon, and without oceans absorbing heat, Venus became thermally isolated. Its surface temperature stabilized, not at comfort, but at extremity. Venus does not cool because it cannot. The mechanisms that allow planets to breathe heat in and out were lost long ago. What remains is a surface fixed in time, where every moment resembles the last, and where heat has become permanent. The extreme heat of Venus did not begin as an extreme condition. It emerged through a process that started gently and then lost control. The greenhouse effect itself is not unusual. On Earth, it plays a quiet and essential role. Certain gases in the atmosphere allow sunlight to pass through, warming the surface. That surface then releases energy as infrared heat. Greenhouse gases absorb part of that heat and slow its escape, keeping temperatures stable enough for liquid water and life. On Venus, this same process followed a different path. Early in its history, Venus likely received only slightly more sunlight than Earth does today. That small difference was enough to push surface temperatures upward. As temperatures rose, surface water began to evaporate. Water vapor entered the atmosphere, and water vapor is itself a powerful greenhouse gas. This created feedback. More heat produced more water vapor. More water vapor trapped more heat. Each step reinforced the next. Scientists describe this process as a runaway greenhouse effect, a situation where warming no longer slows itself and instead accelerates. As the atmosphere thickened, carbon dioxide accumulated. Unlike Earth, Venus lacked active plate tectonics to recycle carbon back into the planet's interior. Carbon dioxide remained in the air, building layer upon layer of heat-trapping gas. Over time, the atmosphere became dense enough to dominate the planet's energy balance completely. Eventually, temperatures rose beyond a critical threshold. Liquid water could no longer exist on the surface. Without oceans, Venus lost its most effective heat regulator. Water molecules in the upper atmosphere were broken apart by ultraviolet radiation from the Sunday hydrogen escaped into space. Oxygen reacted with surface materials. The planet became permanently dry. From that point onward, cooling was no longer possible. the greenhouse system had locked itself into place. Incoming energy and trapped heat reached a balance only at extreme temperatures. Venus demonstrates that planetary climates do not always fail suddenly. Sometimes they drift steadily past a boundary they cannot return from. A runaway greenhouse world is not defined by violence or chaos, but by stability taken too far, where change continues until only one state remains. The atmosphere of Venus is not simply thick, it is heavy in a way that reshapes the entire planet's behavior. Carbon dioxide makes up almost all of the Venusian air. This gas is familiar on Earth as something light and invisible, exhaled quietly with each breath. On Venus, carbon dioxide accumulates into a vast column, extending high above the surface. Gravity pulls this mass downward, turning gas into weight. This weight defines the planet's environment. Near the surface, the atmosphere behaves less like air and more like a slow-moving fluid. Objects do not rest in empty space, but sit beneath a compressive force that presses from every direction. The sky itself becomes part of the surface conditions. Carbon dioxide is especially effective at trapping heat. Its molecular structure absorbs infrared radiation efficiently, the same kind of energy emitted by warm rock. On Venus, heat leaving the ground is captured by carbon dioxide molecules, which then re-emit that energy in all directions. Much of it returns downward, reinforcing surface temperatures. The density of the atmosphere ensures that this process happens everywhere. Heat does not pool in one region and escape in another. Instead, it circulates slowly but thoroughly, smoothing temperature differences across the planet. Day and night blur together. Latitude loses importance. The entire surface settles into the same thermal state. Historical understanding of this atmosphere developed gradually. Early telescopic observations in the 19th century revealed thick cloud cover but offered little information about conditions below. Only in the 20th century did spacecraft measurements confirm the overwhelming dominance of carbon dioxide and the extreme pressures it produced. This composition also explains why Venus lacks familiar weather relief. Winds can be strong, yet they cool nothing. Movement redistributes heat, but cannot remove it. There is no pathway outward, only rearrangement within a closed system. Carbon dioxide on Venus does not merely surround the planet, it defines it. The gas shapes temperature, pressure, circulation, and long-term stability. What might seem like an invisible component becomes the most powerful geological force on the planet, exerting its influence not through motion or violence, but through mass and persistence. High above the surface of Venus, the environment changes in appearance, but not in outcome. Thick clouds stretch across the planet, forming a continuous layer that reflects sunlight and brightens the planet when seen from space. These clouds are composed primarily of sulfuric acid droplets suspended in the upper atmosphere. From a distance, they create the illusion of protection. Light scatters, shadows soften. Venus appears calm, almost luminous. The reality beneath those clouds is unchanged. The cloud layer sits far above the surface, separated by kilometers of dense, hot atmosphere. Sunlight that penetrates this layer still reaches the ground. Once absorbed, the resulting heat cannot escape. The clouds reflect incoming energy, but they do not release trapped heat already within the system. Sulfuric acid clouds form through chemical reactions driven by sunlight. Sulfur dioxide, released from the surface, rises into the atmosphere, where ultraviolet radiation breaks it apart. The fragments recombine with water vapor and oxygen to form sulfuric acid. Gravity pulls these droplets downward until heat causes them to evaporate again, sustaining a continuous chemical cycle. This cycle creates one of Venus's most striking contrasts. At cloud level, temperatures and pressures are closer to Earth-like conditions. Instruments passing through this region experience far less stress than those reaching the surface. Yet below, conditions grow steadily more extreme, layer by layer. Early observations in the 20th century misinterpreted these clouds as signs of oceans or rainfall. Only later measurements revealed their corrosive nature. Rain does occur on Venus, but it never reaches the ground. Sulfuric acid droplets evaporate as they descend, leaving the surface untouched and unchanged. The clouds also play a role in Venus's slow atmospheric motion. They circulate around the planet in just a few Earth days, far faster than the surface rotates. This movement redistributes energy, but cannot remove it, reinforcing the planet's thermal uniformity. The sulfuric acid clouds of Venus demonstrate how appearance and function can diverge completely. What reflects light and suggests moderation instead supports isolation. Above the hottest surface in the solar system, a bright ceiling floats, not as shelter, but as part of the system that keeps the heat below locked in place. Beneath the stillness of Venus lies a restless interior. The planet shows little surface motion, yet heat continues to rise from within. On Earth, much of this internal heat escapes through plate tectonics. Large sections of the crust move slowly, collide, and sink back into the mantle. This recycling releases energy and regulates volcanic activity over long timescales. Venus does not operate this way. Its surface behaves as a single, continuous shell. Without moving plates, heat accumulates below the crust. Over time, pressure builds within the mantle. When that pressure becomes too great, magma forces its way upward through fractures, producing volcanic eruptions that can be vast in scale. The surface of Venus bears the marks of this process. Radar mapping in the late 20th century revealed enormous volcanic plains, shield volcanoes hundreds of kilometers wide, and circular features known as coronae. These structures form when hot material pushes upward, warping the crust before cooling and settling back down. Volcanism on Venus may not be constant. Instead of frequent small eruptions, the planet likely experiences long periods of buildup, followed by widespread resurfacing events. During these episodes, large areas are covered by fresh lava, erasing older terrain and resetting the geological clock. This helps explain why much of Venus's surface appears relatively young. Crater counts suggest a large-scale resurfacing occurred in the recent geological past, possibly within the last few 100 million years. The planet does not gradually renew itself. It renews itself all at once. Volcanoes also feed the atmosphere. Gases released from the interior, including carbon dioxide and sulfur compounds, replenish the thick air above. Without plate tectonics to trap carbon in rocks, these gases remain aloft, strengthening the greenhouse effect. In this way, Venus's volcanoes do more than reshape the surface. They connect the interior to the atmosphere, maintaining the conditions that define the planet. Heat rises, gases accumulate, and the cycle continues. Venus demonstrates that a planet does not need moving plates to be active. Energy finds its way out regardless. The result is a world where stillness at the surface hides deep and persistent motion below. Time behaves differently on Venus. The planet turns, but it does so slowly and in the opposite direction of most worlds in the solar system. Venus rotates from east to west, a motion known as retrograde rotation. The sun would appear to rise in the west and set in the east. More striking than the direction is the pace. One full rotation takes longer than Venus needs to complete an orbit around the Sun. A single day on Venus lasts longer than its year. This extreme slowness reshapes the planet's interaction with sunlight. On many planets, rapid rotation distributes heat through alternating day and night. Venus does not rely on this mechanism. Sunlight lingers over the same regions for extended periods, yet surface temperatures remain nearly uniform. Rotation no longer governs climate. The atmosphere compensates in unexpected ways. High above the surface, winds circle the planet far faster than the ground below. This phenomenon, known as atmospheric superrotation, allows the cloud layer to complete a full circuit in just a few Earth days. Energy is moved sideways rather than vertically, smoothing temperature differences without cooling the planet. The cause of Venus's backward spin remains uncertain. One explanation involves a massive collision early in the planet's history, altering its rotation. Another suggests gradual slowing due to atmospheric tides created by solar heating. Over time, these forces may have reversed the spin entirely. What matters more than the cause is the consequence. Slow rotation weakens magnetic field generation. Without a strong global magnetic field, Venus is less protected from the solar wind. Charged particles interact directly with the upper atmosphere, contributing to the gradual loss of lighter elements over long timescales. This unusual sense of time reinforces Venus's stability. Long days do not bring cooling nights. Seasons are minimal. Change arrives slowly, if at all. Processes that depend on cycles and contrasts are muted. Venus shows that rotation is not merely a detail of motion. It shapes atmosphere, climate, and planetary evolution. By turning backward and barely turning at all, Venus removes time itself as a balancing force, leaving heat and pressure to define the planet without interruption. For much of human history, Venus and Earth were grouped together. They are similar in size, mass, and overall composition. From a distance, they appear like siblings formed from the same material at nearly the same time. This similarity makes their differences more instructive than their resemblances. Venus shows what can happen when small shifts in balance are allowed to persist. Earth maintains a climate shaped by moderation. Oceans absorb heat and release it slowly. Plate tectonics cycle carbon between the atmosphere and the interior. Water As temperatures rose, water evaporated. Once oceans were lost, regulation failed. Carbon dioxide accumulated. Heat intensified. Each step reinforced the next. The planet did not cross into catastrophe abruptly. It drifted there. This is why Venus is often described as a warning, not because it predicts a specific future, but because it demonstrates a principle. Planetary systems respond to feedback. When reinforcing loops dominate over stabilizing ones, outcomes shift permanently. In the 20th century, climate science began to recognize this parallel. Studies of Venus helped clarify how greenhouse gases influence temperature over long timescales. The planet became a natural laboratory, illustrating extreme versions of processes that also operate on Earth. The comparison does not imply inevitability. Earth and Venus are not the same system. Differences in distance from the Sun, rotation, magnetic field, and geological activity matter. Yet the underlying physics is shared. Energy enters, energy leaves. The balance determines everything in between. Venus reminds us that habitability is not guaranteed by size or position alone. It emerges from continuous regulation. Once that regulation fails, recovery may not be possible. Seen this way, Venus is not an alien exception. It is a familiar world that reached an unfamiliar outcome, offering insight not through drama, but through contrast. There was likely a time when Venus did not resemble the world it is today. Evidence suggests that early in its history, conditions on the planet may have allowed liquid water to exist on the surface, creating an environment far more moderate than the one observed now. At that stage, Venus received more sunlight than Earth, but not enough to immediately eliminate oceans. Climate models show that with a thinner atmosphere and fewer greenhouse gases, surface temperatures could have remained stable. Under such conditions, water would have persisted, collecting in lowlands and interacting continuously with the atmosphere. If liquid water was present, it would have regulated the planet's climate. Oceans absorb heat and release it slowly, reducing extremes. Rainfall and evaporation move energy across the surface, forming feedback loops that help maintain balance. Over long timescales, these quiet processes determine whether a planet remains habitable or drifts toward instability. Water also affects geology. When liquid water reacts with volcanic rock, carbon dioxide can become locked into solid minerals. On Earth, this process limits atmospheric carbon. If similar reactions occurred on early Venus, they would have slowed greenhouse gas buildup and delayed warming. Evidence for ancient water comes from the ratio of hydrogen to deuterium in Venus's atmosphere. Deuterium is heavier and escapes less easily into space. The unusually high ratio measured today suggests that large amounts of hydrogen were lost over time, consistent with the evaporation of oceans. As the sun brightened, this balance shifted. Higher temperatures increased evaporation, water vapor accumulated, and because water vapor traps heat efficiently, warming accelerated. What once stabilized the climate began to amplify change. Eventually, liquid water could no longer survive. Without oceans, Venus lost its primary stabilizing mechanism. Ultraviolet radiation broke apart remaining water molecules, allowing hydrogen to escape into space. The loss was permanent. This transition unfolded gradually over hundreds of millions of years. Venus crossed a climatic threshold beyond which recovery was no longer possible. The planet was not always hostile. It became so through slow change, leaving behind a dry world that still bears the imprint of a wetter past. Life depends on continuity. On Venus, continuity was lost long before conditions became extreme. If Venus once had liquid water, it may also have briefly offered environments where simple chemical processes could persist. Water enables molecules to move, collide, and react. It stabilizes temperature and provides time. These factors do not guarantee life, but without them, life has no opportunity to begin or endure. As temperatures rose, this window narrowed. Increasing heat accelerated chemical reactions beyond stable ranges. Water evaporated more quickly than it could return as rain. What had been a surface-based system shifted upward into the atmosphere, where conditions were less predictable and more exposed. The loss of oceans marked a critical transition. Without large bodies of water, Venus lost its ability to buffer environmental change. Temperature swings intensified. Surface chemistry became dominated by dry reactions. Nutrient cycles that depend on liquid transport ceased to operate. Atmospheric changes compounded the problem. As water vapor accumulated and then vanished, ultraviolet radiation from the sun broke apart remaining molecules. hydrogen escaped into space. With it went the raw material needed to rebuild water. This was not a temporary setback. It closed a pathway permanently. Venus also lacked protective systems that helped preserve habitability. Its slow rotation weakened magnetic field generation. Without a strong magnetic field, the upper atmosphere interacted directly with the solar wind. Over long timescales, lighter elements were stripped away, further drying the planet. These processes unfolded gradually. There was no single extinction event. Instead, environments became less stable, then briefly hostile, then uninhabitable. Any early biochemical activity would have faced shrinking refuges and increasing stress until persistence was no longer possible. Life on Venus did not fail because conditions became dramatic. It failed because the conditions required for stability disappeared. Habitability depends not only on temperature or water at a moment in time, but on the ability of a planet to maintain them. Venus lost that ability, and with it, any chance for life to continue. Venus marks a boundary for human exploration. It is a place where technology does not gradually improve outcomes, but instead encounters firm physical limits. Reaching Venus is not especially difficult by interplanetary standards. The challenge begins after arrival. Heat, pressure, and chemistry combine to overwhelm systems designed for far gentler environments. On the surface, electronics fail within minutes. Mechanical components seize as materials soften and seals deform. Cooling systems, so effective elsewhere, become ineffective when the surrounding air is hotter than the machinery itself. Attempts to overcome these conditions have shaped mission design. In the 20th century, Soviet landers sent to Venus were built like pressure vessels, with thick walls and minimal moving parts. Their purpose was not long-term operation, but brief survival. Success was measured in minutes of data transmission, rather than days or years. This limitation contrasts sharply with exploration on Mars or the Moon. There, technology can adapt incrementally. Better insulation, improved power systems, and autonomous software extend mission lifetimes. On Venus, improvements yield diminishing returns. Each gain is offset by the same unchanging extremes. The difficulty is not only endurance, but complexity. Advanced instruments generate heat as they operate. More capability means more internal stress. Simpler systems last longer, but provide less information. Designers face a trade-off where sophistication shortens survival. Recent proposals explore alternative approaches. High-altitude balloons and aerial platforms could operate in the upper atmosphere, where temperatures and pressures are closer to those on Earth. These concepts avoid the surface entirely, accepting that direct contact may remain out of reach. Venus demonstrates that not every world can be mastered through engineering alone. Some environments resist sustained presence, regardless of preparation. In these places, exploration shifts from control to compromise. The planet reminds us that technology is powerful, but not absolute. It advances within the boundaries set by physics. Venus stands as one of those boundaries, defining not how far we can travel, but how long we can remain. Venus occupies an unusual place in human attention. It is close, bright, and easy to see in the sky, yet it often remains absent from conversations about exploration in the future. Part of this silence comes from difficulty. Venus does not reward persistence in the way other planets do. Mars invites long-term missions, gradual improvements, and the possibility of extended presence. Venus offers none of these. Its surface resists habitation, study, and even prolonged observation. Interest fades when progress cannot accumulate. There is also a narrative reason. Human exploration is often framed around movement and expansion. Stories favor journeys that continue forward, places where effort builds towards settlement or return. Venus interrupts this pattern. It allows arrival, but not continuation. The story ends quickly. Scientific focus has followed this tendency. Resources flow toward destinations where technology can remain active and adaptable. Venus demands extreme specialization for limited results. Each mission answers questions, but closes few chapters. The planet does not invite repetition. Cultural imagery plays a role as well. Mars appears rugged and distant, a frontier shaped by challenge. Venus, once imagined as lush and Earth-like, revealed itself as hostile and static. When expectations collapsed, attention shifted elsewhere. Yet Venus is not unimportant. It simply offers a different kind of insight. It teaches through constraint rather than opportunity. Its lessons are not about expansion, but about limits. In avoiding Venus, humanity does not reject science. It follows momentum. The planet remains nearby, unchanged and unresolved, waiting without urgency. Venus does not compete for attention. It persists quietly, holding answers that do not promise comfort, progress, or easy continuation, but clarity about how planets fail to remain welcoming. Terraforming is often imagined as an act of addition. Add air, add water, add time. Venus challenges that assumption. To change Venus into a temperate world, the first task would not be construction, but removal. The planet's atmosphere contains far too much carbon dioxide. Its pressure and heat are consequences of sheer atmospheric mass. Any attempt at cooling must begin by reducing that mass on a planetary scale. Proposed ideas illustrate the difficulty. Some suggest chemically binding carbon dioxide into solid materials, turning gas into rock. Others imagine removing atmosphere directly, either by transporting it away or by triggering reactions that lock carbon permanently into the crust. Each concept requires energy and materials far beyond any existing or near-future capability. Cooling alone would not be enough. Without oceans, Venus lacks a natural system for regulating temperature. Even if surface heat were reduced temporarily, the planet would struggle to maintain stability. Long-term habitability depends on feedback mechanisms that redistribute energy and prevent extremes. Venus lost those mechanisms early in its history. Rotation presents another obstacle. Venus's slow backward spin weakens its ability to generate a strong magnetic field. Without magnetic protection, a newly formed atmosphere would remain vulnerable to erosion by the solar wind. Any gains could be gradually undone. Some proposals shift focus away from the surface entirely. Floating habitats in the upper atmosphere, where temperature and pressure are closer to Earth-like conditions, avoid the hardest problems. These concepts accept Venus as it is, rather than attempting to remake it. The question of terraforming Venus ultimately becomes a question of scale. The forces that shaped the planet operate over millions of years and involve the entire atmosphere, crust, and orbit. Human engineering excels at local change. Venus demands global transformation. Terraforming Venus is not impossible in principle. Physics does not forbid it. But the gap between what is allowed by nature and what is achievable by civilization remains vast. Venus stands as a reminder that not every world can be reshaped to fit human needs. and that adaptation may sometimes mean choosing where not to intervene. Venus is not unique in the universe. As telescopes began detecting planets around other stars, worlds resembling Venus appeared again and again. Many of the first exoplanets discovered were large and close to their stars. These planets orbit tightly, receiving intense radiation. Surface temperatures rise quickly, atmospheres thicken. Conditions drift toward extremes, similar to those seen on Venus. Astronomers refer to some of these worlds as Venus-like exoplanets, not because they match Venus in detail, but because they share its defining outcome. A runaway greenhouse effect dominates their climate. Heat becomes trapped. Cooling pathways disappear. The planet settles into a stable but hostile state. Venus provides a nearby reference for interpreting these distant observations. When scientists measure atmospheric composition, density, and temperature on exoplanets, Venus offers a known example of how certain signals combine. High carbon dioxide levels, inflated atmospheres, and extreme surface heat are no longer abstract data points. They describe a process already understood. This perspective has reshaped the search for habitable worlds. Planets once considered promising, based solely on size or location within a star's habitable zone, may in fact be closer to Venus than Earth. Distance from a star alone does not determine habitability. Atmospheric evolution plays an equal role. Some exoplanets may have crossed their critical threshold early. Others may still be approaching it. Without detailed observation, the difference is difficult to detect. Venus demonstrates that a planet can appear stable for long periods while drifting toward irreversible change. In this way, Venus extends far beyond the solar system. It becomes a template. By understanding how Venus reached its current state, astronomers gain insight into countless distant worlds that may share the same fate. The universe likely contains many planets that resemble Earth in mass and composition, yet resemble Venus in outcome. Venus teaches that planetary failure is not rare. It is a common result when balance is lost, repeated across stars and galaxies on a scale far larger than our own system. Earth and Venus began with striking similarities. They formed from the same region of the early solar system, at nearly the same time, from similar materials. Their sizes, masses, and internal structures remain closely matched. From a distance, they appear like parallel outcomes waiting to unfold. What separates them is not a single dramatic factor, but a narrow margin of difference. Slightly more sunlight reached Venus, slightly more heat accumulated. These small advantages compounded over time, pushing the planet toward instability. On Earth, several systems act together to counter warming. Oceans absorb excess heat, clouds reflect sunlight, plate tectonics recycle carbon from the atmosphere into the crust. Liquid water connects all of these processes, allowing energy and material to move and reset. Venus lacked one or more of these stabilizing links. As temperatures rose, water evaporated faster than it could return. Once oceans thinned or disappeared, carbon dioxide remained free in the atmosphere. Heat increased further. Feedback loops shifted from regulating to reinforcing. This transition illustrates a critical concept in planetary science. Habitability does not depend on perfection. It depends on margins. As long as stabilizing forces outweigh destabilizing ones, a planet can absorb change. When that balance tips, even slightly, outcomes diverge rapidly. From orbit, the difference between Earth and Venus can appear subtle. One is blue and reflective. The other is bright and cloud-covered. Yet beneath these appearances lie fundamentally different energy systems. Earth releases heat. Venus traps it. This fine line is not fixed at a single distance from a star. It shifts with atmospheric composition, rotation, geological activity, and time. A planet can begin on one side and slowly cross to the other. Earth and Venus demonstrate that planetary futures are not guaranteed by origin. Two worlds can start alike and end in opposition. The space between them is narrow, defined not by extremes, but by balance, maintained or lost. As the search for planets expanded beyond the solar system, a pattern began to emerge. Worlds similar to Earth in size and composition appeared to be common. Worlds that remained Earth-like over time appeared to be rare. This contrast suggests that failure is not an exception in planetary evolution. It is a frequent outcome. Many planets begin with favorable conditions, only to drift away as feedback processes reshape their climates. Venus offers a nearby example of this trajectory. Across the galaxy, planets form under a wide range of conditions. Small differences in stellar output, atmospheric composition, or early water content can alter long-term outcomes. When stabilizing mechanisms weaken, reinforcing feedbacks take over. Heat accumulates, atmospheres thicken, surfaces become inhospitable. Astronomical surveys indicate that many rocky planets orbit close to their stars. These worlds receive intense energy early in their histories, increasing the likelihood of runaway greenhouse states. Others may form farther out, but lose water or magnetic protection over time. The paths differ, but the result often converges. From a distance, these planets may still resemble Earth. Their mass, radius, and density fall within familiar ranges. Yet beneath those similarities lie climates shaped by loss rather than balance. The distinction is difficult to detect with limited data. Venus helps clarify this ambiguity. It shows that a planet can retain Earth-like dimensions while following a radically different evolutionary path. Habitability is not encoded in size alone. It depends on how a planet manages energy over billions of years. In this broader context, Earth appears less typical than once assumed. It occupies a narrow corridor where stabilizing processes continue to operate together. Outside that corridor lies a wide population of worlds that resemble Earth briefly, then diverge. The universe may be filled with planets that almost became Earths. Their histories are not marked by sudden catastrophe, but by gradual imbalance. Venus stands among them as a reminder that planetary failure is common, quiet, and written into the long arithmetic of climate and time. Habitability is often described as a destination. A planet is placed inside a zone, meets a set of conditions, and becomes suitable for life. Venus shows that habitability is not a location, but a balance that must be continuously maintained. On geological timescales, planets are never static. Energy arrives from a star. Heat moves through atmospheres and interiors. Materials cycle between surface and depth. Life, if it appears, depends on the stability of these exchanges, rather than on any single favorable moment. Venus likely occupied a habitable state briefly. Temperatures may have allowed liquid water. Chemical cycles may have operated. For a time, the system functioned. What followed was not sudden collapse, but gradual drift. Small imbalances accumulated. Feedbacks that once regulated climate began to reinforce change instead. This reveals a central truth about habitability. It is fragile not because it is rare, but because it is conditional. It persists only while multiple systems align. Water must remain available. Atmospheric composition must stay within narrow limits. Geological activity must recycle material without overwhelming the surface. None of these factors act alone. Venus lost this alignment. As water diminished, regulation weakened. As greenhouse gases accumulated, heat increased. Each loss reduced the planet's ability to recover. Eventually, the system settled into a new equilibrium, stable but inhospitable. Earth remains habitable, not because it is exempt from these forces, but because balance continues to hold. Oceans, atmosphere, geology, and time still work together. This cooperation is not permanent. It is ongoing. Seen from this perspective, Venus is not simply a failed Earth. It is a record of how close habitability always is to disappearance. The boundary between living and lifeless worlds is thin, shaped by feedbacks rather than by design. Venus stands as a quiet conclusion. Worlds do not lose habitability through catastrophe alone. More often, they lose it by drifting beyond balance. Life depends on the rare ability of a planet to remain within that balance, moment after moment, over deep time.